Right, so this is a differentiable function, and you have that the second derivative is and is good for all those x's, right? All right, so that's the one you're talking about, right? Yes? Yeah, okay. So they're saying something about f. They're asking you something about f. Okay, so the first question is, there's a critical point. Fix this. Oops. So x equals c is a critical point of f. And it's located between 5/2 and I guess it could be strictly between and 2π3. Determine whether there is a local maximum, local minimum, or neither at x equals c. Okay. There's a few things you can do. One, if you have a critical point, and let's say it's a local maximum, it's because it looks like this, or it looks like this, or like this, or one of those, right? If it's a local maximum or relative maximum. Okay. So if the derivative exists, the next derivative, right? So if and the function is differentiable. So you don't have this case and you don't have this case because it says to you the function is differentiable. For corners, there's no derivative. So the function is differentiable. So you must have this case if this is a local maximum, right? So if it's a local maximum, what must happen with the second derivative at this point C? What should the value of the second derivative be? Well, second derivative talks about concavity. So if you have a little bump upwards, nice and smooth, because the derivative exists, right? The second derivative must be negative. So that tells you this is negative, right? If the second derivative is positive, that means the graph is pointing upwards. So at this point, you must have a minimum. So since you have a second derivative, you need to figure out what is the value of the second derivative, positive or negative, at C. And you'll say, how can I do that? That's a good question. I don't know what C is. Well, you kind of do a little bit, right? You're told a little bit something about C, and that's probably strict inequalities. So where is this number C? That's above 90 and less than 2π/3. So if this is a circle, 90 is here, right? 2π/3 is how many degrees? It's which quadrant? It's in the second quadrant, right? 2π/3 is 120 degrees. So they're telling you that the C is an angle in here. So it's big, bigger than 90, but not as big as, let's say, 3π/4. It's just right there in the second quadrant. Right there in the second quadrant, you know something about the sine and cosine. You know the signs for all those points, the signs are positive, right? Signs are these coordinates, the y coordinates, and the cosines are all negative, but you know a little bit more. So you know at this part of the circle, again, this is 30, so that's 2π/3. So your angle is in here somewhere. If your angle was all the way there, then the x coordinate, which is the cosine, would have been -1/2, right? But it's not, it's in here. So the cosine is one of those numbers, negative. The sine is a big positive number. It's one of those numbers, right? For all those angles, the sine lives here. So the sign is a number that's above square root of 3 over 2, between square root of 3 over 2 and 1, right? So you have the second derivative. You can just figure out which sign is going to win here, right? So this is negative. This is positive. So this whole quantity is going to be what? This term. Positive or negative? Negative. Sign is positive, but you have a negative in front of it. So this whole quantity is also negative. So you're adding two negatives. So the answer is negative. So if the answer is negative, then you know for sure the second derivative is telling you at this point where you have a critical point, the function is concaving down, right? Second derivative negative, that means you have concavity downwards. So that means right there you have a what? What kind of critical point that is? Maximum. So I'm not sure, Renee, so don't send me direct messages, but so send it to everyone. So I don't know what you mean critical point be 0, 2, 3. They're not telling you what the critical point is. They're telling you the critical point is some number between pi over 2 and 2 pi over 3. Okay, and they tell you that the function is twice differentiable. So you definitely don't have corners at the critical point because you have a derivative everywhere, right? So you don't have corners. It's nice and smooth graph because the function is differentiable. The first derivative exists everywhere. Second derivative exists everywhere because it's twice differentiable, right? So everything is nice and smooth. So if you have a critical point, it's not because the derivative doesn't exist. It's because you have a little bump up or a little bump down, or you have a flattening happening, right? So there's three reasons why would you have a critical point. One, you have a little flattening, the derivative is 0, this way or that way, right? One this and one this, if the graph is smooth. You can't have those because it tells you the second derivative is negative. If you have those flattening outs, at this point, the second derivative is 0. And that's not what you have. Second derivative is definitely negative. So you have one of those cases, and you don't have that. Second derivative is negative. You definitely have this. Okay. Okay. But never send me, Renee. I already mentioned that. Never send me direct messages. Send it to everyone. So part B. Let's see. Find the open intervals where f is concave up. Okay, so part B you should be able to do because, well, you have a second derivative. Second derivative again is negative sign plus something cosine plus this. And of course, if somebody's asking you for critical points or inflection points or concavity or increasing, decreasing, you want the derivative to be factored. So you factor the thing, right? So sine x, so you have 2 cosine x minus 1. This is equal to 0 if sine x is equal to 0. And there are many cases on the circle where sine is equal to 0. Well, more than one. And or this is equal to 0. That is cosine x is equal to 1/2. There are two places from angle 0 to 2 pi, excluding, because it says excludes 0 to 2 pi. Those are excluded. So those are not part of things that you should worry about. So there are two places on the circle, not including 0, all the way to 2 pi, not including 2 pi, where the cosine is 1/2. Cosine is 1/2 here. And it's 1/2 if the angle is pi over 3, 60 degrees, always right below. That's not negative pi over 3 because negatives are not allowed. So you need to get here the long way. Okay. Now the whole circle has 6 pi over 3s. So this is one less. So that's 5 pi over 3. So this gives you two inflection points, pi over 3 and 5 pi over 3. And this gives you, well, let's see. Are there any places on the circle where the sign is 0? Yes, here, but we're not allowed to use that. Either 0 to pi, we're not allowed, but there's also here. So x is equal to pi is another inflection point, maybe potential inflection point. So these are the three that you need to put between 0 and 2 pi. So pi over 3, pi, and 5 pi over 3. And then figure out the sign of the second derivative between these. Right, so the second derivative, again, in factored form, is sine 2 cosine x minus 1, right? So up to 60 degrees, so in here, cosine and sine are both positive, and that's an issue because there's a -1 there, so you need to figure out what's going on, right? So up to that many angle, that much angle, 60 degrees, the cosine starts at value of 1. Cosine here is 1, but you're not allowed to use that number, all the way to a half, okay? So all the way to a half. So the smallest value the cosine gets is a half, right? So when the cosine, of course, is a half, it's right here. So the second derivative is 0. We're interested in what's happening here to the sine. So everywhere else underneath pi over 3, right? Underneath pi over 3, the cosine is more than a half. More than a half means the 2 cosine wins is more than 1. Yes, more than 1, right? So this wins. This is already positive, so the answer is positive. Those will tend to change sign as you move along from interval to interval. So if you're not sure what the sign is, just pick an angle, like pi over 4. Just plug it in. And out of it, take the sign and put the sign in the right interval. So over here, pick an angle between pi over 3 and pi. It doesn't matter which one. So I'll pick pi over 2 because it's easy. Yeah, right? It's easy. Pi over 2 makes this 1. Pi over 2 makes this guy 0, minus 1. So the answer is negative. Those will tend to change sign. Again, between pi, 108 degrees, and 5 pi over 3, which is all the way here, I'm going to pick this angle because, again, it's easy. I quickly know the sines and cosines, right? You could have picked 5 pi over 4. That's also easy. So 3 pi over 2. The sine is -1, cosine again is 0. So you have another -1. So sure enough, the answer is positive. So concave up, concave down, concave up, and then you pick the last one. That requires slight more work, but can you do it? Yes, pick a small angle, right? You can think of it in terms of a negative angle, doesn't matter, right? So I'm thinking of negative pi over 4, or I'm thinking of 7 pi over 4. Right, it's the same angle, takes me in the same place. So pretend I'm somewhere here. So I pick an angle whose sines and cosines I know, like 7 pi over 4, which gives me the same sine and cosine as negative pi over 4. Both the sines and cosines are negative, they're the same negative number, so negative number for sine, 2 times negative square root of 2 over 2, minus 1. Okay, here, clearly the answer is negative, times a negative, so, okay, so that's stays positive. Yes. What am I saying? That's positive. That's positive. That should be negative. Yeah. So they're all inflection points. This is an inflection point. X equal pi is an inflection point. This is an inflection point pi because the signs change values. Okay. And you can tell from the table where the function is concave, the graph is concave up or down. Okay. I guess that was from last year, that problem. So let me, so let me do 3. Just give me one time. So let me do 3, 4. Somebody asked, what's 3, 4? All that. Right. So the function is 1 over x to the third minus 3x squared. Since I detest the question rule, I'm going to write it as x to the third minus 3x squared to the negative 1. And if you want to know where a function is increasing or decreasing, you need to take a derivative. So I'm going to use the chain rule, bring the power down, write the quantity to 1 less power, and then multiply by the derivative of the inside. So 3x squared minus 6x. And I'm going to write it without negative powers because I want to know the sign of the derivative. So negative, this is the numerator, and I'm going to factor it. So 3x, and I'm left with an x minus 2. Over that stuff, which are being squared, which is great. Anything that's being squared or fourth power, I need to ignore it. I don't have to look at it when I'm thinking of signs. Anything squared cannot be negative, right? So whatever this is, squared, I don't care about it. But because the negative here, and they can confuse me, or I can forget it, I'm going to write the numerator, putting the negative inside. So 2 minus x. So the derivative is 0 when the numerator is 0. Therefore, x equals 0 could be a critical point as long as it does not make the function undefined. So the question I ask, is it in the domain? Because if it isn't in the domain of the function, I shouldn't talk about it. And the other potential critical point is x equal 2. So again, the question I have to ask, is this in the domain? So I'm going to go back to the original function. So one of those numbers is not in the domain of the function. Which one would that be? Right, 0 is not in the domain of the function. Right. So then ignore that. You will have that. You will have a kind of either inflection point or critical point that's not going to be that. You always have to think of the domain constantly, of the function, right? So everything else, well, not everything else. Let's see what else is bad. So if I factor the denominator, it gets x squared, x minus 3. So something else is bad. X cannot be 0 and x cannot be 3. So 0 is bad, 3 is bad. So those have to show up on my table. That's also something you're going to have in the exam. You're going to have something that's not really a critical point. It's nothing, not an inflection point, but it's not in the domain. It's all by itself, not in the domain. Everything else around it is good. And because it's all by itself, not in the domain, it has to show up on your table. Okay? So, and then here's the 2. So now when you figure out the derivative signs, you need to include both the 0, the 3, and the 2. Yeah, they're not critical points. Critical points have to be in the domain, but they need to be on the table because the sign of the derivative can change around a hole. And x equals 0 and at x equals 3, you have either a hole or a big jump. You have a discontinuity. So the sign of the derivative can change around a discontinuity. Although there's no other critical point to the left of 2, you might have 2 different signs for the derivative to the left of 2, right? So again, the derivative looks like this. So I don't have to worry about the denominator. It's always positive, right? It's not negative. So I'm just going to plug in one test point, another test point, another test point, and another test point. right? One to the left of 0, like negative a lot, that gives me negative. Negative a lot is going to give me positive. So the answer is negative. So the function is decreasing. I'm going to pick something here, like 1. That's positive, and that's going to be positive. So that's going to be positive. So the function is increasing. So notice the function is going down, and then it goes up. Down doesn't mean does this, because you have an issue here. You can't cross. So down means right there at x equals 0, the graph goes boop, because it's trying to avoid that. And then it comes back up from here. Okay, comes back up. And pick a number between 2 and 3. That's positive. Between 2 and 3, that's going to be negative. So I have negative. So it comes back down. Here I do have something nice. Right? Here I have a local maximum. Because before you say this is a local maximum, this is a local minimum, you keep on looking at the domain, right? Make sure this thing you're going to mention is in the domain of the function. And then pick a number like gazillion. Put it in, positives, definitely negative. So that's also going to be negative. See, the sign of the derivative did not change here. We don't know what's going to happen. So that's going to be downward, so it comes down. So around 3, which is an asymptote, the graph goes to the left of 3 this way, and to the right of 3, it's coming from above. Okay, this is what's happening at 0, and this is what's happening at x equals 3. Yeah, absolutely. Both for, if you're looking to see where a function is increasing, decreasing, or concave down or concave up for the graph, you need to include inflection points for the concavity, critical points for increasing, decreasing. And in both cases, if they are like singularities, single discontinuities, right? Like one point by itself, not good. And another one here all alone, not good. Those have to be included in both tables, both for concavity and increasing, decreasing. Right? Otherwise, you would, if I did this, 2 is a critical point, then I only have to pick one test point to the right and one to the left. Let's say I pick this one and that one. So I have plus, minus. So that means the function is always increasing and always decreasing. No, wrong. That's wrong. It's not always increasing to the left because look, it's going down much further to the left. And it's not always, well, it is always decreasing, but it's not always decreasing continuously, like this graph shows. It decreases, it stops, and then it decreases again. It jumps. Yeah, if the derivative doesn't exist, you have critical points as long as they are in the domain of the function. This particular one had no such issue. The function here looked like this. The derivative looked like this. Is it the third? Oh, -1. Yeah, the derivative looks like this. So you have potential critical points when the derivative does not exist. The derivative does not exist when x is equal to 0. Oh, it's not in the domain, so ignore it. And also when x is equal to 3, you check here, not in the domain, so ignore them. So the only things that make the derivative not exist are the same things that make the function not exist. So you ignore it. Right? These are the same numbers. You didn't gain a different denominator. This is the same denominator with just a new power. So whatever you think will make this derivative not exist, these numbers are not going to be in the domain. So you can just ignore that. Okay. Yeah, so that was and what was the other problem? 11 or something. I don't remember. Okay, let's do 11. Somebody asked, I think it was 11. Was it? 311. Yes, I'm gonna do 311 and then the other one. Okay, let's do 3-2. I'll do 311. After I do 3-2. It's just whoosh, be shorter. Okay. Sorry for the noises. I can't help it. My computer is alive. So find the values of C that satisfy the conclusion. Okay, guys. Okay. 2 is a good problem. So let's do that. Yeah, carefully. So mean value theorem says, under certain conditions, so you say, what are the conditions? Well, function has to be differentiable. Do you really care? No, because if somebody says under what should C be? So for the conclusion of the mean value theorem, blah, 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 blah. That means the conditions, the hypothesis of the mean value theorem are satisfied. The function is differentiable, but don't worry about the hypothesis. So if somebody says use mean value theorem, you use it. You don't worry, but is the function differentiable? Okay, so the mean value theorem says under certain conditions, function is differentiable and continuous on an interval. So the derivative exists on a particular interval. You have, oh, that should be open. It's fine. Okay, so you have a function. So it says that on interval AB, so under certain conditions, the function is differentiable, the derivative exists, and the function is continuous, right? Whether it's increasing or decreasing or increasing and then decreasing doesn't really matter. It says if you take the endpoints, BF of B and AF of A, and connect them, that line will have a slope. The slope will be F of B minus F of A over B minus A. The theorem says if the function is nice and smooth, like this is, there are no corners except at the ends, and continuous, then there will be a point on the graph of the function, and it looks like maybe it's around here, maybe. Not on the very top, where the, no, maybe a little higher, where the tangent line, let's pretend like that, has the same slope, is identical to this. So the tangent line has this slope, the derivative at this point. So there will be a point C where the derivative, that is the slope of the tangent line, is equal to this number. So here you have two cases. This is really the same problem. I'll do one. So one function, let me do the second one. Yes, it hurts. So the interval is 2, 4, right? So I don't know what the graph looks like. We don't care. This point is going to be 2f of 2. And this point is going to be, I'm not saying the graph looks like that. It doesn't. 4f of 2, f of 4. So what are those numbers? So 2, if you plug in 2, you get 4, 2 squared times 2. So that's going to be a half. And if you plug in 4, unfortunately, you're going to get 4 to the 4th. So it's going to be 1 over 16. Right? If you connect those points, that's not what it's going to look like. It's going to be going downwards. But anyway, the slope of that line, it's called the secant line, is going to be f of 4. And you can put f of 2 first. It doesn't matter. Put whichever one you want. If you want to put the bigger one, that's fine. It really doesn't matter. F of 2. But whatever you do here, you need to do the same thing on the bottom. So 4 minus 2. Okay. So I'm going to Put those numbers. F of 4 is 1 over 16. F of 2 is 1 over 2. 4 minus 2 is 2. And I simplify the thing by using common denominator. So then I have 16 over 2. And then I have 1 minus 8, clearly negative. So this is going to be equal to negative 7, 16 times 2. And this is equal to the derivative at some particular x, at least one of them. It could be more than one. So I need to find the derivative. Again, the function was 4 over x to the third. I'm about to take a derivative, so I'm going to write it this way. Okay, so the derivative is negative 12. It's unfortunate. X to 1 less power. So now I'm going to bring this down. So it tells you for a particular x that it's so special, we call it C. So for particular x, this number is equal to that number. So you set those equal to each other and solve for x very slowly. And when you solve for x, you don't have to simplify. So, okay. So first, let's get rid of the negatives. So cross multiply. So x to the fourth is equal to 2 times 16 times 12 divided by 7. Right? So x, I'm about to undo an even power. When you undo an even power, what do I have to put here? That's an even power. Positive, negative, right. Positive, negative, and whatever the stuff is, which I'm not about to simplify, but go back and you check the domain. You can give them a C or an X that's not in the domain, right? Domain's a big issue here throughout this chapter. So you go, normally you would say, this is it, circle, move on to the next problem, but you go check and you say, wait a minute, domain did not include any negative numbers. Okay, it doesn't. So really, this is not the answer. The answer is the positive root or whatever you found. And trust me, what you found is probably going to be the correct thing. I mean, it's going to be correct unless you've done a calculation mistake. Yeah, absolutely don't simplify. Because when as I said in class, if you simplify and it's incorrect, any mistake will be graded. So, you want less of that opportunity for mistakes. So since you don't need to do the next step, simplification, don't simplify. Okay, so the other problem is the same. The other part in part A, the other part of A. So let's do B. B is slightly different. Yeah, okay. So B says the derivative of a function is always between -3 and 4. Again, mean value theorem says under certain conditions, the conditions are satisfied because it says the function is differentiable, right? Under certain conditions, the derivative is going to be f of b minus f of a over b minus a. And what are b and a? Usually are the endpoints. But can you pick two other points instead? Can you pick those points? Yeah, you can call this a f of a and call this b f of b. The function is still continuous here and differentiable. You can take another interval, whichever interval you want to, right? So it tells you the derivative, they're telling you, which is this number, is between -3 and 4. That means this number is between -3 and 4. So between -3 and 4 is this number. For any a and b you choose. So they give you a value at one point. They say g of 1 is equal to 5. You can call this your a, or you can call this your b, or do whatever you want. Call them a or b, the 1. So you have 1, 5, you have a point on the graph. So you have 1 point on the graph, 1 point, right? And they're going to ask you something about another point. So one of the points is where your x is equal to a, and the other point is going to be where your x is equal to b, right? And you have a choice. Which one's your a, which one's your b, doesn't matter. So they give you a point. So there must be another point somewhere, and there is. There is g of 3 they're asking you. So they're saying, can you tell me something about g of 3? What's the maximum value? And it's like, okay, are you asking me something about x equal 3? The answer is yes. So one of them, x equal 1 and x equal 3, one of those two is going to be your a, the other one is going to be your b. So again, let's, I don't know, let's make this the b, the f of b, okay? So a f of a is going to be 1 point, and b f of b, again, it doesn't matter which is which. It's going to be your other point, 3 comma, let's call this f of 3. Okay. So now I know f of b minus f of a over b minus a is a number between -3 and 4. So f of b, which is this, which I know nothing about, minus f of a, which is 5, over 3 minus 1 is a number between -3 and 4. Very slowly, I solve the inequality. And the only thing you have to worry about, number 1, set it up. Number 2, if you were to multiply the inequality throughout, or divide the inequality throughout by a negative number, you need to make sure you flip the direction. So I need to get rid of this 2 by multiplying throughout by 2. 2 is positive, so I don't flip the direction. 4 times 2 is 8. And I want to solve for that, so I'm going to add 5 in both sides. So I have -1 less than or equal to f, all sides. F of 3 less than or equal to 15. So now the question is, can you tell me the maximum possible value of f of 3? So what's the maximum possible value of f of 3? 15. You do the same thing with the other point. Again, you have f of b minus f of a. B minus a is a number between -3 and 4. And they give you, again, they gave you the 1, 5. That's 1 point. It can be your b f of b or a f of a. Doesn't matter. It's up to you. And the other point has x coordinate -2, just for fun. So don't know why I did that. Maximum is equal to what? Okay. So whichever. So let's make this, I don't know, let's make this, let's keep this the a f of a and make this the b f of b, right? So this is going to be your f of b. So then again, I go here. This, again, it doesn't matter which one you choose. I'm going to choose this to be my unknown, just to keep it in the same place. This is going to be the same thing I had before. The f of 1, which happens to be 5. So this is going to be your -2, and this is going to be -1, right? So I'm going to write -3 less than or equal to f of -2 minus f of 1, which is 5, -2 minus the x coordinate at 1,5, which is 1. Yes, less than or equal to 4. So I need to say something about this number. So I need to solve the inequality for this unknown. So again, slowly, the denominator here is negative. And this is where things can go wrong. You look at this, you're in an exam, somebody sneezes next to you, and you end up with negative, I don't know, or positive or -1 here. That's the answer. Sad, but you know, things happen. So you gotta go careful. You know, you gotta be careful. Do and redo these calculations. Anyway, so when you get rid of it by multiplying everything by -3, because you want to get rid of this. When you multiply by -3 throughout, that's a negative number. You need to change the inequality, the direction. So you're gonna have 9, and of course, don't forget to correctly figure out the sign. Multiplied by -3, so I get -12. Okay, and I'll get rid of the 5. So I have f of -2 is a number between whatever this is and whatever that is. So now if somebody says, what's the maximum value for that? I will say that is 14. That's the maximum value. Okay. If they ask what's the minimum value, clearly it's -7. Okay, so that's a standard. That's a nice little problem in an exam. So what was the other one? 11. Okay, so let's do 11. So we have a box. So this is 2x, that's x, and that's h. What's h? Okay, fine. So the volume is, you're stuck with it. It has to be 18. The unit you don't really care for until you're ready to answer questions. Then you go back, check for your units and put the correct units. So the length of, okay, so the length and the width and the height are those. So you need to cover the box with something. So material for the top and base. So the top and base, the material will cost is very expensive. So for this part and this part cost $12 per square meter, right? For each piece like that. And for the sides all the way around, only 6. So all the other sides, right? All the way around, 4 sides. It's going to be $6 per square meter. So let's see. So they're going to ask you something about the cost. Right? Write the equation for the cost function. Okay. So cost is cost of top and bottom plus cost of sides. Right? So if the top was 2 square meters only, each one of those 2 square meters will cost you $12. So 2 times 12. If it was 24 square meters, it would be 24 times 12. If it was 3.5 square meters, it would be 3.5 times 12. So you have no idea what it is. You know it's exactly 2x times x square meters. So the top and the bottom, for that matter, they look the same, right? 2x by x, right? This is x here. So have area 2x times x, not plus x. So it's 2x times x, which is the same as 2x squared, each one of them. So area is 2x squared. Area here is 2x squared. So the cost for the top is going to be the amount of square meters times the cost per square meter. So it's going to be 2x squared times 12. The cost here is going to be 2x squared times 12. The cost for the top and the bottom is going to be the sum of those. So 24 plus 24, so that's a lot of x squares. Right? So top and bottom cost is going to be 48x squared. And now we're going to do the sides. So the sides don't all look the same. Those two look the same, right? So those two have base x and height h. So the area for each one of those two, same thing here, is x h area. Okay. So therefore the cost is going to be 6 times that. And the same thing here. So those two sides, when you add the cost, it's going to be 6 of those plus 6 more of those, so 12 of those, right? Left plus right is going to be 12xh, right? And now we're going to do the 2 other sides, the front and the back. I'm not going to shade the back. It's already a disaster. So the front has base 2x and height h. So the area is 2xh. The back is the same. Back there is 2xh area. So the cost here is going to be 6 times that. And the same thing here. So each one of those is 12xh and another 12xh. So front and back is 12 and 12xh. So it's going to be 24xh. So the total cost, that's your C. I'm not going to write C of x because what I'm going to write after the equal sign is not just x's. It's going to have h's. So I can't write this. I'm just going to call it C for now. So it's going to be that much plus those two, and I can add those two, right? So that's 36. Okay. This is not a multivariable course, so you need to somehow get rid of one of the variables. So this is where the given, the constraint is useful. You're told that whatever x and h's are, the volume has to stay constant. So the volume is the product of the 3 dimensions. 2x is one dimension, x is the other dimension, and h is the other dimension, the constant, and that is constant. So x squared h is equal to 9. So you can solve for h. I'm not about to solve for x because I don't want to root anywhere. So I'm going to solve for h. So this is 9 over x squared. So I'm going to use this here to write c as a function now of just x. So the h is 9 over x squared. Okay, so I'm going to rewrite it, simplify. You don't have to multiply those, avoid it. Times 9. Do simplify the x's because you're about to take a derivative. 1 over x. Okay, and they're going to ask you to minimize the cost. Right? Nobody's going to say maximize the cost. So you want to take a derivative. The derivative is going to be 2 times 48. Right? You don't have to write 96 there. Just leave it. X. The derivative of this piece is going to be negative 36 times 9, 1 over x squared. And we want this to be equal to 0. And there are a number of ways of doing that. Well, you can combine those fractions into 1, or you can just separate things. So I'm going to separate things. It seems slightly easier. Cross multiply, right? So I have 2 times 48, x to the third is equal to 36 times 9. So x to the third is equal to 36 times 9 over 2 times 48. And now I'm going to try to simplify a little bit. So I have 6's. 6 goes here and here. Goes 8 times and goes 6 times. And simplify slightly further. Right? I could have simplified by 12. Anyway, goes 3 times and this goes 4. So that's all I can do. So I have 27, or I can leave it. X to the third is equal to 3 times 9. 2 times 4. How convenient is this? Because you have a cube, right? Both of those, numerator and denominator, are perfect cubes. So therefore, x is equal to 3/2. So you have 1. Of course, I didn't mention the domain, did I? No, didn't mention the domain. Domain is important here. But this is a product. You're told that 2x squared h is equal to 18, right? And you have a function in terms of x only. Clearly, x cannot be 0. It's in the denominator. Plus, you don't want a box that doesn't exist. One dimension 0. So if you really, really have to, you can say x starts at 0, put an equal, but really it doesn't, right? You will have a box, but if you forget and make it No, closed, that's fine. I won't penalize anybody. And then how big can X get? We did a problem very similar to that in class. Oh yeah, definitely. Yes. The pictures will be given to you. Yes. So how big can X get? Anything? What's the domain? 9. So I cannot make X that number. I cannot find an H that will do this. No? Any number. Any number positive, right? Yes. X and H can be anything. In this case, I'm only interested in X because the function is in terms of X. So any number would work because this is a product. This is not like this. If I was like that, I would say, okay, X can get as biggest when this is 0, and then I can figure out the largest value for X. But that's not it. It's not a sum. It's a product, so it can be anything. So 0 to infinity, which is kind of good news. So that means your table starts at 0. Really, it's not going to be 0. Goes to infinity, and you have one critical point, which I forgot, perhaps. And what do you need to do? Minimize. So the function better have a minimum. So it better go this way and that way. So you just quickly say we did it. Don't have to. It will go that direction because it will have a minimum there. That will be it at X equals 3/2. Right, and then you go ahead and figure out the rest of the dimensions. Right, so this was the X. This was 2X, so that's 2 times this. So that's going to be 3. And this was the H. And remember, H was, what was H? 9 over X squared. So this is equal to 9 over this number squared. Again, I would leave it like that. I would even do it this way. I would write it this way, which is correct. Don't simplify anything in the exam. Unless you absolutely have to, like when you want to figure out what the critical point is, so you can position it to the left or to the right of 0, to the left of 1 or whatever, you need to know exactly approximately what kind of number it is. There I would simplify a little bit. But this type of things, don't simplify. So when then the question asks for dimensions, remember when you give the dimensions, you go and read the problem to attach, is it meters, is it feet, right? So what was the number? Is that 3 feet, 3 meters, 3 inches? Just put the dimensions there. And of course, they have to be the same dimensions, right? Questions? Oh, yeah. Yeah, so that was good. You should do that problem. Didn't we do something like that in class? I remember. I think I gave that something like that in the workshop. But I don't remember that. Maybe. What are you saying to me? Oh, yeah, but don't do it this way, Minji. I see what you're saying. So suppose somebody gives you acceleration. We have a problem with that. Where is it? No, I didn't put one. Oh yeah, I did. Problem 1C. So 1C says, didn't I also give something like that in the in the quiz? Oh yeah, in the quiz last quiz. Yeah. Fine. So, so you have that. So instead of, if somebody says find this, so this is a second derivative, this thing. This will be the first derivative. And this will be the function. So I wouldn't go ahead and integrate. Well, I would, but I wouldn't go ahead and integrate and say this is -1/2 cosine of 2t. Please don't use substitution because supposedly you don't know it. And then say this is v, and therefore s, I need to integrate that. I wouldn't do that. Because then you have to write plus ct plus d. Yes, you would. I wouldn't do that until I first find c. Right, so here they give you a sub t is equal to sine of 2t. And I want you to find velocity. Velocity is the integral of the acceleration. So you're saying to yourself, okay, what function has as derivative sine? Well, that's cosine. Well, not really, because the derivative of cosine is not sine, it's negative sine. That's not negative. So that means the function itself must have the negative. So that's negative cosine of 2t. But that also doesn't work, plus c. If you take the derivative of this, that gives you negative, derivative of cosine is another negative. So it gives you positive sine 2 times the chain rule, an extra 2 factor, which that doesn't have. So you need to undo the 2 factor. This will automatically give you. So how do you undo it? By putting a -1/2. So the answer, the velocity is -1/2 cosine of 2t plus c. Whatever you think the antiderivative of sine is, write it out. Even if you're not sure, just write it out and take the derivative of this thing slowly and check that it's correct. If it isn't, change your answer, tweak it so it works. Okay. So now that you have that, you look at the problem. Before you find the position function s of t, you see if they give you some information to figure out what c is. And they do. They say v of 0 is equal to 0. So when t is equal to 0, v is 0. So I'm going to plug those things in here. The t's are going to be replaced by 0. Here's only one t, and the v is going to be replaced by 0. So 0 is equal to -1/2 cosine of 0 plus c. Cosine of 0 is 1 times -1/2. So -1/2 plus c is equal to 0. So c is equal to 1/2. So now that you find c, you write v correctly. And now you can go ahead and find s by integrating that. Okay. So again, the function that gives you as derivative 1/2 is 1/2 t. And you check the derivative of 1/2 t. Is it 1/2? Yes. So that works, right? And then since we don't know substitution yet, you're not allowed to use substitution. So guess an antiderivative, that is, guess a function that you need to write here, whose derivative is this thing. So the derivative has cosine, so the function must have sine. The argument, that is the stuff inside, should not change. Don't mess with that. So you see, can I just leave it like that with nothing else? Well, let's see. The derivative of sine of t, the question is it equal to -1/2 cosine of 2t? Well, let's see. The derivative of sine is not negative, number one. It's positive. It is cosine of 2t times the chain rule times 2. That's not good. First of all, this has a negative, so I need to stick a negative here to make up for it, because the sign is not going to create the negative. The derivative of sine doesn't create a negative, so how was the negative created? It must have already been there. And because this has a 1/2, the answer has a 1/2, and this derivative will generate a 2 factor. I need to put another number here. In here, I need to put a number, so that number times 2 is exactly -1/2. So that number must have been -1/4. So I need the -1/4 here. So I check -1/4 sine of 2t is the derivative correct. Correct means this. So it's -1/4. Derivative of sine is cosine of 2t times 2. Sure enough, the answer is exactly what I want, right? So once you have s of t, which is this plus a new c now, you check to see if there's some information in the problem that would allow you to find this new constant. And there is. It says if you plug in 0 for t, you should get the position of 2. So I'm going to plug in 0 for t. This t and that t are going to become 0. And the s is 2. So 2 is equal to -1/4 sine of 0 plus 1/2 times 0 plus c. Sine of 0 is 0, 1/2 times 0 is 0, so c is 2. So s then is -1/4 sine of 2t plus 1/2 t plus 2. Okay? Yeah. Yeah, because you're done. So as long as you don't, right, so I wrote C, that's temporary, done, over with. It doesn't exist anymore. See, you don't see it here. It's gone. That part of the problem is erased. And now I have a new problem. Here's V fine S, so I can write C. This is a different C. If you really worried, call this C1 and call this C2, but it doesn't matter. What you're not allowed to do is have this say plus C and then keep it, I don't know, like 4 sine of t plus c, let's say. And then say that don't find it because you don't feel like finding it yet. And then do this. And then write something horrible here. Something plus ct plus another c. That would be death. That's bad. Don't do that. Yeah. Okay. So 3/7. 3/7, which one? B. Ah, yeah, B. What's that? What's that number 1 there? What is that? 31. I mean 31. That's terrible. That's not 3 and then 1 hanging out. It's a x to the 31 in the power. And the same thing. Oh my goodness. Yes. So find the limit. So the limit. Yeah, that's a good problem. You should do this one. Okay, so any function that has x's, 2 x's, x's on the base and x's on top, and limit, whatever, you check. And you really need to check what the answer looks like. But most likely, this is going to give you indeterminate form. You're not allowed to stick a log there unless you show the person who's reading it that you could not evaluate the limit, that this is indeterminate form. So that's important not to skip that part, right? So you kind of plug in. So you get 0 plus 1, that's 1, right? 1/0 is what? Infinity. So you say, oh, that's indeterminate form. Why? Because 1 to any number, like 4 and a bunch of 9s, is still 1. 1 likes to keep things at 1. 1 to negative whatever actual number is still 1. -9999, still 1. Right? 1 wants to keep things at 1, but the power of infinity wants to, expand things, make them huge. Right? So who's going to win? We don't know. So that's the indeterminate form. It's a tug of war here. Right? So you need to write this. before you say, look, I can't do anything. Please let me use some log. And I'll say, go ahead. Right? But you first have to write this. This has to be there. So now you say, take the log of this thing. So instead of finding the limit that they gave you, you're going to find the limit of the log. And here, just go ahead and separate those. The power comes down, and it's going to be 1 over x to the 31 log 1 plus 4x to the 31 limit. Do not forget this. Anyway, so make it a fraction, because anytime you take a log, you're going to use L'Hopital's. It's about to happen. You can't avoid it. All those cases eventually will use L'Hopital. So you need a fraction. So you keep on working until you have a fraction. Don't you dare put that in the denominator. That's going to be a disaster. Don't do that. That's bad. This is already in the denominator. Write it there. And now you're going to use L'Hopital's. And when you use it, say you're using it. That's all you have to write. Show that you're using it. So L'Hopital says take the derivative of this separately, stick it in the denominator. So that's going to be 31x to the 30. And then take the derivative of this separately, put it in the numerator. So the derivative of log of stuff is 1 over stuff times the derivative of the stuff. And I'm going to put that in the numerator. So 1 over the stuff times the derivative of the stuff, which is going to be 0 plus 4 times 31 times x to the 30. No need to multiply 4 times 31 and get 99, for example. Right? You don't want to just throw points away like that. Don't multiply. So now you simplify. All that goes away with all that. It's how do you simplify? You create fractions. Those far away things go in the numerator as a product. The inside things go in the denominator. And then you're going to plug in. Don't plug in yet. You could plug in, but I'm not going to. It definitely you don't want to plug in when this is still here. You need to get rid of those, right? So if I were to create a fraction before I simplified this stuff and that stuff go in the numerator. So 4 times 31 times x to the 30 goes in the numerator, and all that as a product goes in the denominator. So 31x to the 30 times this stuff as one piece. Don't multiply. So now I'm gonna, if I didn't simplify already, I'm gonna simplify now. The main thing you need to simplify is this. So now I'm gonna plug in. So the 0 is gonna create the 0 here. That remains and that remains. So I'll have 4. But that's not the answer to the question. The question didn't say find the limit of that. You stuck a log there that you shouldn't have. Well, you shouldn't, it wasn't there. So you need to undo the log. What do you mean natural log of 1? No. It was supposed to be 31. The one that's sticking there. Didn't I? Yeah. Unless, well, the file I'm looking in one of my 2 classes has a 3 and then 1 on the side. I meant to put 31 so you guys don't do anything weird with the small number. So there's a 1 there hanging out. That's supposed to be there. It doesn't matter. If you want to do no. I'm not sure what you're saying. Natural log of 1 is equal to 4. It's not. So I don't know what you're saying. Right, so the limit is, so the limit with the natural log is 4, so the correct answer, so we have find the limit of the function as x goes to 0, and you said, oh, forget, I'm not doing that. So you're saying I'm gonna do something else for you. How about if I do that? And I'm like, awesome, but can you please give me an answer now? So what would the answer be? Somebody said it. Right, you need to undo the log. So you take an e that undoes the log and put the answer on top of it. So that's your answer. Right? You found the 4, don't forget the next step. Because the question was not this. This is what you did. The question was this. Right? So you just make sure you take the answer and put it on top of it. What's this? Let's see, hold on just a minute. Yeah. Right, so let's do that. So this is a nice problem. So we have, that's supposed to be an equal sign, it's missing. Okay, so x squared plus 5. And when you look at this, first thing, when somebody says concavity, you know, increasing, decreasing, inflection points, critical points, like, okay, you'll say, hold on, what was the domain? You always start with a domain. The question's not going to be there, find the domain, but that's the first thing you need to do. Find the domain of the function. And it says to you, oh, look, the function is twice differentiable from negative infinity to infinity. That means I already did it for you. The function is differentiable, domain's everything. It's twice differentiable, domain's everything. It says, don't worry, everything is allowed. So everything is allowed. Second derivative is, so when you find potential critical points and potential inflection points, the potential critical points, you bring them all in. There's nothing to exclude. And the potential inflection points, you don't know if they're inflection points. You need to put them on the table to make sure that the sign changes around them. Then they're inflection points, right? So if that's the derivative, you have critical points when the derivative does not exist, or the derivative is equal to 0. Well, the derivative is equal to 0 if the numerator is 0. So that means x squared is equal to 5. That means x is equal plus or minus root 5. So your table should have negative root 5 and should have positive root 5, and the derivative really likes those numbers. The derivative looks at the domain and sees only 3 intervals, right? It sees this one, and this one. It doesn't see more. There will be more in a second, but the derivative sees only 3. Because the only nice points for the derivative are those 2. Nothing else is interesting, right? Now, if there was something that was not in the domain, you would have to include it. But everything is in the domain. Right? The domain's everything. So does the derivative not exist? So is there a particular x that makes the derivative undefined in this case? No, right? I mean, look at the denominator. It's a sum of a square plus a positive number. So this is not 0 ever. It's at least 5. So nothing else to worry about. So then we look at the second derivative. Inflection points have to satisfy more than those 2 conditions. The second derivative has to not exist, or the second derivative is 0, and sign of derivative changes, flips from positive to negative or negative to positive. So whatever you find here, you need to include it on the table, and then you'll be able to tell whether it's an inflection point or not. You can't tell just because it's in the domain, as you would for a critical point, right? Line down here. Okay. So the second derivative exists always. So the second derivative is 0 when the numerator is 0. The numerator is 0 if this is 0. So that has to be included. That's an interesting point to the second derivative. First derivative doesn't even see the 0. It's like one of those other numbers, right? Ignores it. And also two more, right? X squared is equal to 15, so x is equal to plus or minus square root of 15. You should be able to position them correctly. So you say square root of 5, square root of 15, well, square root of 15 is bigger. Same thing on the other side. Okay, these are numbers that are interesting to the second derivative only. So for the first derivative, you really have to do any number here, any one number here, and any one number here, right? So if I pick a number like gazillion, whatever sign I get here, let's say positive, I'm going to put the same here. So let's put gazillion for the first derivative. I'm going to put gazillion here. This is positive, so I'm not plugging anything there. This is going to be positive too, even if it's a third power, because that's positive. So I'm not going to pay attention to those. So pick a gazillion, put it in here. Certainly I'm going to get negative. So this is negative, that's negative. I put a negative gazillion over there. So I get, sure enough, another negative, 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 because that's one interval for the first derivative. And then I have only one more number to pick. I might as well pick 0. Put it in. I put it in, I get positive. So positive, positive. Now the second derivative has 3 interesting numbers. Has this number, and this number. So it has more intervals to worry about, right? So the second derivative, you need to pick a number here, you need to pick a number here, you need to pick a number here, and you need to pick a number here and plug them in. Absolutely. Yes. Or, oh, let me say something in a second about this table. I don't know, my computer's beeping in. Anyway, so you pick another number here, let's say negative gazillion. You put it in. Negative gazillion means negative. Negative gazillion minus something else. Negative gazillion is going to be huge. Huge squared. That's going to be positive. So negative times positive is negative. So that's negative. You go to the other side. Positive gazillion. Positive gazillion, that's positive. That's still positive, so that's positive. Right? For x equal negative square root of 15 to be an inflection point, the sign here must be positive. It has to change. If it stays negative, it's not an inflection point. Just because you make the second derivative 0 doesn't mean you did that. Right? So you need to make sure, you need to check that the sign changes. The sign will change. The sign will not change if you have something not in the domain. Then the sign may not change as you're jumping on the other side. Otherwise, the sign should change. So you pick a number here, anywhere here in this interval. So I'm going to pick -1 to be safe. It's a number to the left of negative square root of 15. So -1, whatever it may be, probably here, right? But I don't care what it is. -1, I put it into the second derivative, and I get -1 squared minus 15. That's negative. And another negative. Sure enough, that's positive. So positive, positive, because this is the same interval as far as the second derivative is concerned. Second derivative does not see the 0. It's not. Well, it does see the 0. No, that's not the 0. Yeah. So the 0, yeah. The derivative sees the 0, so I'm going to pick a 1. Then whatever that gives me, I'm going to put the signs in both places. One's going to give me positive, that's going to give me negative again. That should change. It will change again, unless there is something not in the domain. Then it may stay the same. So you have inflection point as the sign changes, inflection point, the sign changes, inflection point as the sign changes. Okay, now I want to say something about the table. There are others, including the coordinator. So I've written this table this way. So others might write the table this way. So let's say, oh, look at this interval. Negative infinity to negative root 15. Look at this interval. Negative square root 15, negative root 5. Look at the next interval. Negative root of 5, that's a comma, 0. So they might write it this way. It's slightly confusing to me. If it's not to you, awesome. If it is confusing, when you see something like that, your first job is to decipher it. So you go ahead, start on the left, negative infinity, awesome. Ooh, a number. Let me write it. And then same number, okay, I'll take care of that, another number. Let me write this. So you see a sign, another sign, a sign. So you say first sign, put it here, second sign, I put it there, and you move on. Okay, so decipher it. If you want to write it this way, if you understand it this way, that's perfect. But it could be given to you this way or that way. If it is given to you, it's probably going to be given to you this way. If it isn't, then you're going to be asked to create it somewhere. Or you might be asked to create it somewhere and be given to you in another problem. Oops, what's happening? Yes. Yeah, you can do separate tables. Sure. But yeah, we'll do that. But if somebody says graph something, you want the two tables to be really one, because you can't have, you know, A, B, and then C, B, D, second derivative, first derivative, and you have, you know, some signs and whatever signs here. And then how do you know from where to where, right? It's kind of weird to go back and forth and try to figure out, how do I draw this? Do I draw it this way? Do I draw it that way? Right? Just put it together if you were to ask to graph something. Okay. 3/8. What's 3/8? Okay. So you have this function. This function looks like this. So the graph of A over B plus C x squared it's not the same. But from far away, and if you have a x and y axis with that don't have numbers, it will kind of look the same to you. It will look like this. Right? And the same on the other side, but it doesn't matter. We're on the right side. Does it say? Yeah, the right side. Right. So it kind of looks like that if these are constants, and they are. So this is so a problem like that, which we've done a problem like that in the lecture notes, I think. An easier one. Yeah. Yes, we've done that. So it says you put a box. That was a hexaquadrate, I think. Not a box, like a rectangle. And you ask for the maximum possible area. Right? So this is a point on this hyperbola. So this is x comma y. So x is this big and y is this big. And xy is a point on this function. So y is this much x's. Okay. So the area of this rectangle, so it will be x times y. Right? So area is x times y. Of course, I want to write this a function of one variable, so I'm going to replace y. So that's going to be 5 over 3, that's the y, times the x. There it is, stick the x there, right? So here's y, here's the y, here's the y, times the x, right? So here's the function. We did that in class. You did that in class. So the domain, so now I have a function of one variable. The domain, that is the x's that you're allowed to use, can be as small as what? What's the domain? How big can X be? How small can X be? You can have a rectangle that goes like that. X is smaller. Can have a rectangle that goes like that. X is smaller. 0, right? So you can make it like that, or if you really don't feel like it, it's okay to put, you don't want it tiny little. I mean, you're going for a maximum area, you're not going for 0 area, but you can start at 0, you can close it, it's fine. But you know, the practical domain is really with an open, it doesn't matter. How big can X be? If the rectangle is low, really short, X gets bigger. So how big can it be? The X. Infinity, right? So this is the practical domain, but that's acceptable as well, right? So that's the domain. So you're asked for maximum, so you're going to take a derivative, take the derivative. Unfortunately, we're stuck with the quotient rule. So the derivative of the top, which is 5, times the bottom as is, minus the top times the derivative of the bottom. So the derivative of the bottom is take the power out, write what you have with 1 less power, times the derivative of the inside, which is another 2, over the denominator squared. So square, square. Okay, so you see there is a common factor. There is one of those, there's another one of those, and there's a few more of those. So whatever you do, don't multiply these things. Just get rid of the common factor. So one of these goes away. If you can take the same thing, same factor away from every single term, then you can. Otherwise, if it doesn't show up in every single term, you cannot do it. You can't simplify. But I can simplify because it shows up here. So I take one of those out, I take one of those out, and I take one of those out. Right? So now, what is it doing? So now I'm gonna, it's right, there's only one of those, right? So I multiply away 15, now that I simplified, plus something. This is completely gone. So I have 4 times, you really have to go slow here. Right? If the number is not good looking, you've done a mistake. So minus 20x over stuff. Okay, notice the derivative does not exist for some x, but that x is negative. There's no way for that x to be a negative length. That's not going to happen. So the derivative always exists. There's no negative x's here that are allowed. So you look at the numerator and see when the derivative is 0, so therefore the numerator has to be 0. Simplify the numerator, you get negative 10x plus 15. Okay, number's not very nice, but it doesn't matter. X, that's because I created the problem. That's how you know. So 3/2. So it's not bad, right? So let's say, and then you say the derivative does not exist when the denominator is 0. So x is equal to negative 3/2. Clearly, that's not good, right? It's not good because x is, you can see it, it's on the right, plus it's a length, right? So here you only have one critical point. So what you can't do, put your critical point. You can close it or you can do it dotted, whatever, all the way to infinity. You know you're looking for a maximum area. You will get maximum. It will look like that, so you can go and fake the signs because you know it's going to be maximum. So maximum area, when x, that means this length, is equal to 3/2. So you're looking what the other length, the width is going to be. Y, remember, was 5 over 3 plus 2x 20 squared. Was it squared? Squared. Right? So this is 3/2. So y is equal to 5 over 3 plus 2, 3/2 quantity squared, and leave it like that times, right? Leave it like that. No need to simplify this thing. So here you would have to create the table. You can't just say, I found one number, therefore this is where I have maximum. Well, what if the problem was wrong? What if you get negative and they're positive? Just create a table, put the correct signs, and you're done. Then answer the question. Okay, so that was, yeah. That was 3/8. Any other questions? Three. What's 3/3? Let's do B. Let's do B. 3/3. 3/3 is also good. Yes, I don't know how many times I have to say that. In the first exam, I had one student, I don't know which section, I should have written their name down. There were several students, but one student did it constantly. Well, two students did it constantly, a guy and a girl. For every problem, I said, yes. Can I simplify this? Do I need to simplify this? No, I just said no. Next question. Excuse me. Do I need to simplify this? Ask me this on every question. Don't do that. Don't simplify. Unless the problem says simplify. Don't simplify, right? You simplify, it's going to be graded. Don't do that. Why would you do that? Don't do that to yourself. Don't do it to us. 4 minus, this is a nice problem, yes. Like this one. So what are you supposed to do? Oh, absolute. So that word is a hint. Extrema. So absolute extrema says this is an extreme value theorem problem. That means you're given a function and you're given a closed domain. You are. So that means you're going to find critical points. There's steps, critical points. Second step, include them on a table that looks like this. Here's the endpoints, A and B. Here's A. Here's B. And between, you're going to put all the critical points and then evaluate. The largest number, the largest F value is the maximum. The smallest, not here, the smallest here in the F stuff, is the minimum value for the function. These are the absolute extrema, those things. Okay, but you need to put the endpoints. And you also have to put, in addition to the critical points, anything else weird. For example, if I had a function that looked like this, part of a parabola, and then became a line, and then became something else, I would put these critical points. I will put any critical points that this part gives me. I will put any critical points that this part gives me. I will put the endpoints, that x and that x, but I will also put those x's, this one and this one, the ones where things break up. Because this piece, or it's part of this endpoint, of this piece endpoint, right? This is a kind of a different looking function. These are three functions put together. So I'm going to put all the endpoints for these three pieces, right? So this particular function, when you're asked to write it, you're given the function with absolute value. So if you're going to do anything like a derivative or a limit or whatever, you need to get rid of the absolute value first. So let's get rid of the absolute value. That means you're going to create a piecewise function. So if x is greater or equal to 0, there was no need for absolute value, right? So I would write it without absolute value because x is greater or equal to 0. It can go only up to 2. So from 0 to 2, right? You can write it this way. This is what f is. And that happens to be, you can simplify it afterwards to -8, right? So from 0 to 2. If x was negative, then absolute value of 3x is negative 3x. So negative absolute value will be positive 3x. It's the opposite sign. So when x is negative, this becomes 4 plus 3x plus x squared minus 5x. So this is when x is negative, and x is negative only up to x equal -1. So -1 all the way to x, all the way to 0. In one place, you can include the equal sign, and the other place you don't. It doesn't matter. You can put the equal sign here, or you can put the equal sign here. In one of the two. Don't put it in both. What was that? You have a question? Yeah, just let me finish this. So, so I'm going to simplify that before I take any derivative. So I have negative 2x of 4, so 4 minus 2x plus x squared. So now I'm going to take a derivative. So this is when x goes from -1 to 0. Oops. Right? So remember, when you're finding critical points, you constantly check them against the domain. Constantly. Right? So if I do some magical stuff here for this piece, and I find a critical point, let's say my critical point is 4, will I accept it? Is 4 in this part of the domain? No, I won't accept it. If this piece, when I do whatever I need to do to it, it gives me a critical point of -1/2, will I accept that? If this piece, it gives me this critical point, will I accept this? -1/2? No, because -1/2 is not in this piece's domain. It's somebody else's domain. This piece does not allow -1/2. So you gotta check everything against the domain, right? So how do you find critical points? You take derivative. So you do this work for two separate functions now, the top and the bottom. So the derivative of the top is -8 plus 2x. That's for x between 0 and 2. And between -1 and 0, the derivative is -2 plus 2x. So this derivative, the top part, is equal to 0 when x is equal to 4. Do I accept this as a critical point? No, because it's not in this domain. Even if it was here, I wouldn't accept it. This piece gives me x is equal to 1. How convenient. Do I accept it? No. It is in the whole domain, right? That's why I love this problem. Because it will catch all the people that will just look at the whole thing and don't look at the detail. This x equal 1 came from this piece that only allows those numbers. So you don't accept it, right? So there's only one, whereas there's nothing, no critical point. What's happening? There's no critical point. That was a bad problem. What was I thinking? So there's no critical point. Don't like this one. So if you create a table, then the only numbers you can put are the 0. I mean, not this, yeah, the -1. So remember, the original domain was -1 to 2. So you need to pick -1, you need to pick 2, but you also have to pick 0 because at 0 things change. The function changes to something else. So you need to put the 0. If you had another critical point, you also stick it in, but you can't forget the 0 where things break up. And then you evaluate the function. The largest number is going to be the absolute maximum. The smallest number here is going to be the absolute minimum. Okay. So if that number here, for example, was a 1, then you would, for the top part, you would include it. But you also have to include the 0 and the endpoints of the whole thing. Right, because this piece that has this domain gave you a potential critical point when x is equal to 1, but this piece has this domain. So this piece does not talk about positive numbers, positive x's. Doesn't go there, right? So when you write the derivative, you can't write it this way. You need to include the domains of the two pieces, right? So if you find potential critical point, you check it against each domain. Right? Each piece has its own little domain, so you check those, and then you take the endpoints, right? You take this endpoint, you take not this endpoint, that's not an endpoint. You take this endpoint, take this endpoint, and then you take the additional endpoints where the function changes definition. So that's the additional one, 0. And you include those, and then if you have any critical points, you include those too. Yes, so if you have a function that looks like that, right? There's a reason that the absolute value is there. The absolute value of a number is not negative. So what if the number was negative inside? If the number was negative, the absolute value gives you negative and negative. It undoes the negative by sticking another negative in front of it. So the absolute value of -8 is not -8, it's negative and -8, right? So if the x is a positive number, then there's absolutely no reason for you to put an absolute value sign, because that's just 4x, right? But if x is a negative number, then the absolute value of 4x is negative 4x. So that's how you split it. So if you have a function that says 4x plus some stuff with no absolute values, you're going to break the function stuff plus 4x. You say, I don't need the absolute values if x is greater or equal to 0. Or stuff, and you say, I really want to get rid of the absolute values if x is negative. If it's not positive, then it's negative. If it's negative, in order to get rid of the absolute value, I need to introduce another, change the sign in front of it, right? So that's how you break it up. So if the domain here was, let's say, from -10 to 4, and I say x is positive, I really have to rewrite it. It can be any number. It can be only up to 4, right? So from 0 to 4. And negative means here from -10 to 0. Okay, so if that was negative here already, you keep it as is with a negative. If x is positive, you keep it as is. You just take away the absolute values. If x is positive, you just take the absolute values, write everything as is. If x is negative, you take the absolute values and change the sign in front of it. So this, in this case, will become positive. You just change the sign. Okay, so you split it up, but when you split it up, you write out the domain, right? So if you have an original domain that went from -10 to 4, and you have an absolute value in the function, you check where the 0 is, and here, get rid of the absolute values and do nothing else. Here, get rid of the absolute values and change the sign in front of the absolute value, right? So, so if your function was 2x plus 3 over 4x plus 4 plus sine x or whatever, right? So I would say get rid of the absolute values. If the number is positive, just get rid of them, don't change the signs. And get rid of the absolute values. If that, let's say that was negative here. Get rid of the absolute values and change the signs. So -2x plus 3 over 4x plus the signs only in front of the absolute values, not everything, right? The plus 4 stays, plus sine x stays if this was negative. Yeah, but you need to put the domain next to it, because if you find here a critical point that says -1, it's not here. So if this gives you a critical point -1, you're not supposed to accept it. Right, so you check which piece has what domain. Okay. Questions? What was somebody else asking to do something? Can't remember what it was. All right, so any other questions? You should do every problem in this review. This review, you should do all of it. Everything in this review. You'll have 7 problems in the exam. 7. Of the box. What was the question? The dimensions. Where's that? Oh, that thing. So what were they? X was 3/2. 2x then is twice that, so it's 3. And h, that was 9 over x squared, is whatever that is. It will be 9 over 3/2 squared. So that means the 9 is going to go away with this 9, and the 2 squared is going to go in the numerator. So h is 4. So 3, 3/2, and 4. Okay, so it's going to be specific. No, never, never, never do that. When somebody says find the local, oh, the location, yes. Location, yes. Location, you can give just the x coordinate, or you can give the point. Either is fine. But the question will be specific. Go back to an empty page. Right. So the question is going to say, give the x coordinate of the local maximum. So it's going to be clear. Now, if you forget and you're used to giving points, that's okay. I assume you know which one is the x coordinate, so it's fine. For location, if it just says location or where it occurs, you can give a point. But usually the where or where it occurs or where it's attained, local maximum minimum, that expect the x coordinate. But you can give a point, that's good too. But in this particular example, exam, it will be very specific. It will specifically ask you for the x coordinate. And if it asks you for both, they will say, give the absolute maximum and the x coordinate where it occurs. So that means give those two numbers you're giving me separately. The absolute maximum is f of 2, whatever that is, 4, and it occurs at x equal 2. Actually, you have to give them separately. Okay. Any questions? What do you mean? Can I write an example answer? What does that mean? 3/9 and 3/10. Oh yes, 3/9. Yes. Let's do 3/9. Definitely do 3/9. Yes. So 3/9 is what I was telling you. With I mean, it looks horrific. I don't like the way it looks. The table, but what can you do with it? So you're supposed to graph something. The first thing you do when you're asked to graph, check, is there an asymptote? So there's an asymptote. They're telling you x equal 1 is a vertical asymptote. So what do I have to do on the graph to identify x equal 1 as a vertical asymptote? How do I show that x equal 1 is an asymptote, vertical asymptote on the graph? What do I have to draw? Yeah, what type of a dotted line? Straight line? How do I draw it? That's not the word. Yeah, dotted line how? A vertical dotted line, right? So vertical line. So I'm going to draw a vertical line at x equal 1. Now the graph does not cross vertical asymptotes. Does not. So your graph better not cross this line. So I'm going to dot it. There it is. My graph is not going to cross this line. And then says, it gives me some points. The graph goes from -2 to -1. Another point is 0, 0. So here's a point on the graph, 0, 0. It goes through 2, 0, goes 3, -1, and it goes through 4, -2. Okay, so I'm going to draw those points. So what was that? It was 1. So I go all the way to 4. 2, 3, 4. That's 4. And I go all the way to -2 on the other axis, and -2. So -1, -2. That's -2. And then I go, let's say 1, 2, and 1, 2. Now, if you were asked to do such a graph, you will be given something that looks like that with lines here and points. So you'll be able to graph it semi-exactly, not really. Okay, so now I'm gonna put the points in before I look at the increasing, decreasing. Because once I put the points in, then I'm going to look at the table to see how do I connect the points and without crossing this vertical asymptote. So -1, -2, -1. Here's I already took care of this. -2, -1. So here's a point. 2, 0. So 2, 0. Here's a point. 3, -1. 3, -1. Here's another point. And 4, -2. 4, -2. Here's another point. Oh, I bet you it goes like that, doesn't it? Okay. Yeah. Okay, I see what it is. All right, so now I'm going to look at that terrible table. So it says from -infinity to -2 is negative positive, first, second. From -2 to 1, you have positive, positive. From 1 to 2, this is not a point. This is an interval. From x equal -1 to x equal 2, right? And then you have from 2 to 3, you have something else happening. And then you have more intervals, keeps on going. And then you have more intervals. Okay, then. So you want to go here. The question is, do you go this way? Do you go this way? How do you go there? So you start on the left. You go to -2 downwards, right? Down, facing up. You go this way. Okay, so this says you go this way, and then you go up, and then you increase facing down, increasing facing down, decrease facing down, decrease facing down, decrease facing up, decrease facing up, increase facing up. So that's what I'm going to connect. Remember, I cannot cross the asymptote. So I'm going to draw the graph this way. So I'm going to go to -2, which is here. This way, I'm going to go to -2. Clearly, it came from above. Nobody told me where to cross. I'm just going to cross whatever I want to. They're not telling me how to do it. But they're telling me I need to turn at -2. So I'm turning. And all the way, I go up, 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 all the way to the point 1. Where's 1,2? No, I don't have 1,2. This is not the point. It's confusing. Okay, so I need to go through here. And they're not telling me any changes until 1. No changes until 1. So I'm going to keep on going up, up, up. I'm not supposed to cross it, so I need to be asymptotic. Right? So it's going to look like a weird parabola. Doesn't have to be parabola. Parabolas are symmetric, so it could be like this. You don't know. So it looks like that. Then after 1, this is after 1. After 1, I increase. So how do I increase? I'm not here. I must be down here to increase. And I go all the way to the number 2. The number 2 is here. So I go all the way to the number 2. And what do? I come down when I find 2. So I come down, and this tells me what to do. Goes up, 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 and turns. Goes up and up. And again, it doesn't tell me where to turn, so I'm just going to go across whatever I want to the right of 4, because at 4 is where I turn around again. Also, the graph looks like this. And because the derivatives always exist, you can't have a corner here. Just make sure it's smooth. Same thing here. Make sure it's smooth. Okay. You could go ahead and translate the table. So you have negative infinity. You see the next number is -2. The next number is 1. The next number is 2. The next number is 3. Next number is 4. And then you have infinity. And because you have an asymptote of 1, is the asymptote 1? Oh, the 1 is here. So this is an asymptote. So that's dotted line. And now we'll go and use the signs they gave me in order. So negative, positive, positive, negative, negative, positive, and then positive, positive, negative, negative, positive, negative. No, positive, 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 right? So that tells me how to do it, right? It comes down, facing up, it goes like that. Here's your asymptote. And then it goes up, facing down, and continues to go down, and then finally goes up forever. It doesn't stop going up. And this is an asymptote. So you can see the graph. And now if you take the graph, take it and move it to touch the points they gave you. Okay. Okay. So what was the other question? Was that the whole question? Yeah, so draw this thing. So you're supposed to draw that. 310. What's 310? Oh yeah. So that's kind of similar, but with words. Okay, so that's slightly more, well, maybe difficult, I don't know. So if f is increasing, let's say on the interval from negative infinity to -2, then you know from negative infinity to -2, the derivative is positive, so the function is increasing, right? Increasing means the derivative of this function, right? If I say g is increasing, that means the derivative of this function is positive. That's what it means. If I say something is increasing, its derivative is positive. Okay? So then, if somebody says f prime is decreasing, what derivative is negative? If f prime is decreasing, which derivative is negative? So again, if somebody says a function is increasing, that means its derivative is positive. If somebody says a function is decreasing, that means its derivative is negative. So if somebody says to you, f prime, that's the function. I call it f prime. F prime is decreasing. Which function is negative? The sign of what is negative? F double prime, right? If something is decreasing, its derivative is negative. If something is increasing, its derivative is positive. So if this is decreasing, its derivative is negative. Okay. So if f prime is decreasing from negative infinity to negative 4, that tells me negative 4 better be on your table. I should 2 and negative 2 and 2 and that's it. And 0. What happened to 0? And 0 should be there. So it says the function is this function is decreasing. That means the second derivative is negative on this interval, negative. So negative for the second derivative here, up to negative 4. Okay, so when they're saying to me that f is decreasing from negative infinity to negative 2, and f is increasing from negative 2 to 2, and then they say f prime is decreasing from negative infinity to negative 4. F prime is, and also from 0 to infinity. And f prime is increasing from negative 4 to 0. There's another interval here. 2 to infinity. So I'm going to go pick all the points and all the number x, the interesting x's, negative 2, 2, negative 4, and 0, and put them all together. Something that's not so large. There it is. Okay, so 0, 2, negative 2, and negative 4. So now I'm going to do this. The function is increasing, so that tells me something about the derivative. The derivative is negative on this intervals. So negative here. What happened to negative 2? Oh, that's, I have them backwards. Who knew? Okay. So negative here, and also negative after 2. Okay. And the derivative is positive in between. So I'm done with the first derivative. So this tells me about the signs of the second derivative. So that says the second derivative is negative on this intervals. So after 0 is negative, and to the left of negative 4 is negative. And it tells me the second derivative is positive between negative 4 and 0. So that's the second derivative. So now I can tell what the function is doing. Right? Is decreasing facing down, decreasing facing up, increasing facing up. So it turns around here, right? And then keeps on increasing facing down. Here you have an inflection point. Go like that, and then turns. The concavity changes, and then turns down, facing down. Here you have a local maximum. The local maximum is f of 2, and it happens at x equal 2. Here you have a local minimum. The local minimum is f of negative 2, which I have no idea what it is. Oh, they give it to you. F of negative 2 happens to be negative 3. F of 2 is 3, right? And it happens at x equal negative 2, right? That's the local minimum. This is the local maximum, right? And you can see, oh, let's sketch the graph. You can graph it. So when you graph it, they say there's a vertical tangent line. There's a vertical tangent line at x equals 0. So they give you 0, 0. So at x equals 0, you have a vertical tangent line. So that means the graph does something like this. Either like that, so you have a vertical tangent line, or the other way around. It can bend the other way. So it changes concavity, but it's kind of vertical looking there. That's where the tangent line. It doesn't stay vertical because this is still a function. Every x has not several y coordinates, has one. So it's just one single point there, but it kind of looks vertical around there a little bit. Okay. So, and it could be like that, or it could be turning the other way. I'm not going to do it. We'll see how it turns. Do you have any asymptotes? No, it doesn't tell you anything. It tells you, though, you do have an asymptote. You have, as x goes to infinity, that is on this side of the graph, the y coordinate becomes 1. As you're moving to the right, when you're down, going up and down and doing weird things, maximum, minimums, inflection points, all that stuff, when you're done with all that, that's done in the past, finally you're settling at the height of 1. That's what it's telling you. So how do you settle at the height of 1? You're coming down, you're coming from above 1, and you're settling. Where are you? That's weird. Really? Oh, negative infinity. Okay, that doesn't work. Okay, negative infinity, that's better. So otherwise, that doesn't work. So, okay, so this is better. So you're going to, this is y equal 1. So you're going to y equal 1 like this, right? So you have an asymptote that you're approaching it this way. So your graph goes like that, okay? On the other side, you just go down. There's no asymptote. It doesn't say that there is one. No, there isn't. There's no asymptote. We don't know. Maybe there is. If you want to create one, it will mess up the signs in that that they're giving you, decreasing and increasing. So if there's no asymptote on the other side, so the graph goes down on the other side. So whatever the graph does here, eventually goes down forever. So now you need to connect the rest. So find the points they gave you. So they gave you -4, 0. So find those points. So let's say -4, 0. Oops, -4, 0. That's not possible. Okay, so I need to move this graph much further. So -4, 0, we have -2, -3. So -4, 0 is here. -2, -3. So -2, -3 is, oh, at 1. Okay, not -1. Okay, fine. -2, -3 is here. Here's another point. And then 0, 0, here's another point. And then 2, 3, let's say here's another point. Right, so you have those 3 points. The asymptote is not where I drew it. It's not -1, it's 1. So the asymptote is on top. This point is at 3. So here's that point. So now you need to connect what they gave you. The graph goes like this, down and turns. So down and turns. This is an asymptote. So you're going to go down, you need to touch here, and then eventually it will turn. Where will it turn? Well, let's see. Does it tell you? Yeah, it turns at -2, you have this minimum. So at -2, you have a minimum, and you go up, and you keep on going forever up until you have to turn again, and you turn at 2. And 2 is here. So you go forever up, and you turn at 2. And eventually you go down because there is no asymptote, right? It says keep on going down forever. So the graph's going to look like this. Right, so you put the asymptote, you put the points, and then you follow the signs to connect everything. Without doing the mistakes I just did. And when they're asking you to label is something they're going to ask you to do. So you label. So y equal 1 is a horizontal asymptote. So you label this. You label this. So this is where you have a local minimum is equal to -3. You label this. Local maximum is equal to f of 2, which happens to be 3. right? Label this. If they want you to label inflection points, that's an inflection point. You can see it from the table. Anytime that the sign changes of the second derivative, you have an inflection point. So you have an inflection point at x equal -4. So you have an inflection point. Notice it changes from facing down to facing up. And you have an inflection point at x equals 0. So again, changes from facing up to facing down. It turns around, right? So you label these. So inflection point, it's the actual point, and inflection point. So they ask you to graph it and label. Another thing you have to label is the axis. Label everything. Yeah, I didn't see your answer is yeah, should have been one of -1. Yeah. Okay. Right. So notice when I did a mistake, then I couldn't follow what it told me. So that tells me there's a mistake somewhere. So you need to go and redo everything and check that you've done a mistake. If you can't connect everything, there's something you put wrong on the picture there. This mess. Okay. Any other questions? All right, so again, do every single problem here, every one. And make sure you know what you're doing, correct notation, don't write limit equal and forget the limit sign, don't write weird things. A lot of people did that in the first exam, that was horrible. Limit of f, or let's say, I don't know, x squared plus 1 is equal to x squared plus 1 is equal to 3 squared plus 1. I mean, this is just bad, horrible, right? Don't do that, right? You need to write limit until you actually plug in which case you don't write the limit, right? Never write this. That has no meaning whatsoever. None. This is as bad as writing this. You know, your friend writes this, you look at them like, are you okay? What is that? Right? Don't do that. Don't do that. It means nothing. Now just concentrate on this one. Why 12 problems? There are not 12 problems here, there are 11. Where are the 12 ones? Did I put 12? You can do this one. If there's something, the other one you like to do it. I haven't looked at the other one, so I don't know what's in the other one. Oh, good. Okay. So if there are a lot of questions, I can maybe have another review tomorrow. There's a real need. So you just email me. There's a lot of questions. But you should do all the problems in the review I posted on our site. Some of them have answers, right? A lot of them have answers, some of them don't. But some of them, very similar ones, are in our lecture notes. So if there's something that doesn't have an answer, check the lecture notes. See if there's something there. And that will have an answer. That will have a solution. Okay? All right. Okay. So let's stop right here. Email me if you have any questions, if you need more time. I have some time tomorrow. So yeah, have a good night, everyone. Take some time to relax, eat, sleep, right? And then start again tomorrow. Okay, see you tomorrow, or maybe not. We'll see. Okay, all right, have a good night.